Welcome to, I think, the final research seminar from the Department of Education and Research this year. So we have Siara Isaac, who's going to talk to us about defining what is true engineering-induced conceptions of the nature of knowledge. What we do in these seminars, first of all, is that we each go around the room and just introduce ourselves and say where we're from, so that everyone knows, and there's also a signing sheet that will be passed around that we'd ask you to complete so that we know how many people have come. So I'm Paul Ashwin, Department of Education and Research.
Education and Research.
Sajin Lee, Education Research.
John Taylor, Educational Research.
Jan MacArthur, Educational Research.
Chris Hill, Engineering.
Artist.
Oh, sorry, I'm Gia. I'm doing a graphic recording.
Rebecca Martin, Educational Research.
India Romanenko, Educational Research and Cultural Studies.
Yeah, so visiting from Moscow. Okay, so the other thing to mention is that the seminar is being live streamed. So the first thing to say about that is that microphones are live, so the private conversation that you think is private is probably not private, so just be aware of that, particularly as we work our way through the seminar. And also for those who are joining us on the live stream, if you want to email questions for the discussion part, you can email those to the email address edresseminars, which has 2 S's in the middle, at lancaster.ac.uk. That's edresseminars@lancaster.ac.uk. That's great. So we'll now move on to Siara's talk. Siara is a PhD student, part-time PhD student in this department, as well as working in an education development role at the EPFL in Lausanne. I won't inflict my French accent by giving the full name of the institution, but I'm sure Siara can do.
Thank you. I'm really pleased to be here today. This is the first time that I have physically been in Lancaster. So this will get me out of a lot of awkward situations when people say, "Oh, you're at Lancaster. Isn't it a beautiful campus?" And I nod and So it's fun to actually be on this side of the room and actually understand what I'm actually seeing vaguely throughout the windows when I'm joining at a distance to seminars in this room. This is part of my thesis work. That I guess I'm now in my 4th year of with Paul Ashwin. So it's really useful to know where you're from, a little bit about your background, just in terms of your relationship with math. Yeah, this is a qualitative talk, but none of the examples I'm going to be using rely on sort of an idea of the nature of equations or modeling in mathematics. This sounds hideous or tolerable? Tolerable. Okay, good to know. Okay. My background is actually as a chemist, and not a chemical engineer, simply a chemist. The structure of my talk is going to be, I think that for many of you, you're already translating this idea about students' conceptions of the nature of knowledge into ideas around epistemic beliefs. So we'll look a little bit at some definition of epistemic sophistication and what that looks like in engineering, why that's important. Reviewing 3 models of epistemic sophistication in terms of how they'll be useful for framing this work, briefly the methodology of the study, and then the qualitative results. So engineers are expected to problem solve in really complex situations that involve a number of different factors, often quite a bit of pressure, and that the problem solving isn't the type of problem solving where there are clear right answers or even a single right answer, but there are a number of competing and sometimes contradictory aspects that need to be simultaneously managed and decisions made. So it's not simply about finding a correct answer, but about making decisions about what you're going to prioritize over something else. So what this actually looks like. So for instance, we have an idea of sort of a comment of a lower epistemic sophistication. Baptiste says they give us formula and then we try to apply them. So there are the formula, and our job is to use these static things, the formula, in a real world context. Bart has an idea that these formula aren't simply things, but are clearly coming from observations. That the particular formula in question, that Newton's equations of movement, or Newton's second law, and then the equations of movement coming from that, that there were actual observations that he made, and that then we're identifying what in those observations was actually the relevant parts, and being able to condense that into a given equation. Bernard says that we can find two solutions for a concrete problem, but in a calculation question, no. That given that we have exact numbers that we put into a calculation in black and white, there will be a single answer. So a complete absence of awareness of that calculation being a simplification of reality. That model is not, in fact, a precise, that the equation is not a precise model that holds true exactly. It is a simplified model. But Didier is able to identify that different engineers will see the same problem in a different way, and that they will come up with multiple approaches. In this case, he was talking about designing, I think it's the same in English, a step for fish in a river, and that different engineers may come up with very different solutions, and that they may both be good and reasonable approaches to the problem. So again, so why does this matter? That if you imagine a young engineer who's been employed by the Ministry of Transportation, for instance, who is responsible for making decisions about how this is going to get fixed urgently, and that in discussions with engineers from different consulting engineering firms, that these people seem very expert. They have really different suggestions on what to do and what needs to be done. How is this young engineer going to be making those decisions and deciding which models of these highly abstract ideas are actually applicable here? Is a model, can they simply take a model for pressure and continuous flow situation to model the water flow here? Can they simply take existing models for deciding about the stresses on these steel beams, on these pylons, or do these models not apply in this context? So making those decisions. So there's been previous work, unsurprisingly, on epistemic sophistication in engineering. Paulson and Wells found that engineering students holding other aspects constant compared to students in other areas were more likely to believe that knowledge was simple. That is, that knowledge could be conceived of in the idea that that you can collect knowledge as bricks, rather than knowledge being a web or interconnectedness. And that knowledge was certain. That is, that there were correct answers, single, correct, absolute answers, and that there was that a consistency. Engineering knowledge has been shown to, epistemic sophistication has been shown to increase over studies in engineering. However, it doesn't typically reach a level that would enable them to make really well-reasoned decisions between competing knowledge claims, to actually afford themselves that role of that there is decision-making involved in problem-solving in engineering, that there isn't simply a right answer, and that they're actually able to make those decisions. So I hope that I've convinced you that this is something that is relevant and important. So clearly there's a need here to make sure that engineers are graduating with a high level of epistemic sophistication. So we're going to need a model of epistemic sophistication and a way of actually measuring that in order to assess where students are and how they're moving forward. So William Perry is someone you've met before. His work, not so much. Okay, so William Perry launched the area of epistemic sophistication, or historically he called it epistemology. Epistemology, however, the ology implies an interest in how those conceptions are formed and the belief. So rather just cut it at epistemic if we're just simply interested in the beliefs themselves. So he conducted interviews with Harvard undergraduates, longitudinal interviews. He did have a few women in his sample, but he ended up dropping them all for undisclosed reasons. Primarily, so an exclusively male sample, Belenky, Goldberger, and Tarul took then an exclusively female sample, and Baxter McGolda had a mixed sample. But in each of these, they proposed various stage-based models of moving from that there are clear right answers that knowledge is a dichotomy, it's either wrong or it's right, and that knowledge comes from experts, to a more sophisticated approach that knowledge is constructed and evolving, and that we can develop criteria which will enable us to assess a knowledge claim. That it isn't that it's coming from an expert, but that there are criteria that will enable you to assess the validity of a knowledge claim within a given context. So obviously these nice, rigid, clear models look lovely on paper, but tend to fall apart when we actually start trying to compare them to people's beliefs. And so there's been there's a detour that I won't take you on of some other models that attempted to be quantitative. I've tried to collect some quantitative data. I'm a chemist. I wanted, but I'm letting that go. I can talk about that if you're interested afterwards. But coming back to the stage-based models, because they do work in terms of an overall arc of observed trends, that students do move from here to here somehow. And so I'm going to use an engineering-specific stage-based model developed by Julie Gainsburg quite recently, in which she identified 4 different stages of, and here you'll find very similar to the models previously, dualism around faith in one correct answer known by authority, moving to skeptical reverence, where recognition of the need for judgment in engineering problem solving. So for instance, we have answer key, the only way of checking solutions, for instance, or the instructor. Here it's using mathematical concepts that an internal coherence is sufficient. It's not just simply pure math that you can check within the math within the concepts, and that's how it works. Relevance is when they actually start making connections to the real world. That it's not simply a model, but it's a model. And if I think about, for instance, one of my students here said, well, to check it, I imagine, when you put your hand on the back of a fridge, it's hot. And so thinking about what that meant in terms of how gases, of how the heat is being cycled out of the fridge using the compression cycle. And the skeptical reverence so skeptical reverence actually came from her work with practicing engineers, and was something that she observed very rarely within the students. So she developed this model through think-aloud. 8 students in civil engineering solved their homework in a think-aloud protocol. That is, that they said what they were doing and why they were doing it. And she observed that twice for each student, and then had some interviews with them. So civil engineering students in a single U.S. university. And there's 8 of them. So it seems like a model that seems coherent. But I was interested to see whether or not it transfers to a francophone context, and if it works in a more broader context. The problem with these stage-based models, though, is that it implies that there is a better way to go about thinking about things. That actually taking knowledge as evolving and uncertain is a more sophisticated way to behave, and the best, and something that we should aim towards. However, there are some knowledge claims, some situations in which it is actually more appropriate simply to accept a knowledge claim as absolute. And so from this, this is the final model that we'll look at, Elby and Hammer's cognitive resource model, the idea that sophistication isn't about functioning at a particular level. It's about having an awareness of strategies at that level of sophistication and being able to choose from the range of strategies that in a given context you may employ any of these different strategies, not simply the most sophisticated approach. So being more able is about increased awareness and choice, appropriate choice of strategy. So I'm interested in looking at these 2 models. Is Gainsburg's model applicable in my context? Can I contribute to it? And is Elby and Hammer's more fine-grained approach of not trying to put a student in a box, but trying to say that there are a different range of abilities that I'm looking for, so in my specific context. So so for each of the series of think-aloud interviews that I conducted, there were 4 different tasks. I needed to construct tasks that were sufficiently challenging to make sure that students were using a range of different problem-solving strategies, and that they actually were problem-solving, not just simply calculating, but actually really suffering a bit. I needed to make sure, however, that it didn't require knowledge beyond a traditional first-year curriculum, so that I had students from a range of different backgrounds across engineering, and that they all would have the fundamental knowledge to do that. And I wanted to make sure that these problems were sufficiently contextualized to enable students to make connections, to do order of magnitude checking, to do connection to their lived experiences. So for instance, one of the problems that I had them do was imagine a dental polymerization, and the idea of putting it in the context of a dental polymerization. It was very easy in that problem to make an error in the calculation and come up with a 8 or 9 degree temperature change, which would not be something that you would want. And so to actually see, was it something that they would check to see, does this make sense, or it came out of the equation, so it must be clear. In terms of the interview, it started with a stimulated recall of asking students, what did you do here? Where did this information come from? Your approach. And I was particularly interested in the origins of equations that they wrote down, why they would trust an equation, why it was a valuable equation, and if the limitations and the applicability of models that they were using. So this is an example of a think-aloud task. Here was a chemical explosion with microscopic ash particles at initial velocity. This is completely useless information, but it was really interesting to see how stressed students would be by that. If the information is there, do they have to figure out how to use it? Or was it okay for them to choose a way of solving it that didn't require that information at all? In fact, this problem doesn't require any chemical knowledge at all. It is simply a straightforward ballistics calculation. But again, it was whether or not students were able to see that. It was uncomfortable for them. Perfect. I did 2 series of interviews with students starting from their first year bachelor's to their second year of their master's, from 12 different disciplines, mostly engineering, bioengineering, chemical, civil, electrical, environmental, etc. 2 students from mathematics and 1 student who was doing a master's in technology entrepreneurship, who had a bachelor's degree in engineering. The interviews were conducted in French or English, depending on the choice of the student. And the students are identified in this by pseudonyms of their own choosing, where first-year students are Anna, Amandine, and Antoine. Second-year students, Bart, Baptiste, and master's students start with Didier, Elise, and Guillaume. As you can see, it's just a 2 years master's, but Guillaume is actually starting a second master's with us. He's completed a master's previously, so I've given him a G. Okay, so given that we don't have a model of engineering, of epistemic sophistication engineering that's working, I'm going to have to revise the goal here. We're not going to be able initially to look at how do we actually improve this, but how do we characterize it? What does epistemic sophistication look like in engineering? So we've got these 2 different models to look at, and a measurement situation with the think-aloud protocols with these different tasks. So I'm interested in looking at characterizing students' behaviors in terms of the epistemic sophistication that they represent, to see if Gainsburg's model, if I see the codes from Gainsburg's model, if I see other things, and to see if I see students operating at a specific level, or do I see all students employing a variety of different approaches. Yeah? Okay. So for this think-aloud task with a chemical explosion, I intentionally did not include any formula in any of my equations, but it was really lovely when they actually would write down a clear equation for me, which meant that I could ask them about this equation and where does it come from? What does it mean? And so students came up with a range of different explanations for the source of information that simply came from a sage so long ago, maybe even a Greek. Or I remember the professor explaining it quite well, and I just believed her. I never tried to challenge that. That is absolutely received wisdom. Integrating, proposing that there's an internal coherence to the information with derivatives and integral. Sorry, in English, with being able to take the derivatives and the integrals, and enables us to see that there's a mathematical coherence, and so that makes sense. Or using the units again to check it, that there's an internal coherence, therefore so the equation is reasonable. Actually making a connection to the physical world. It's not just a mathematical coherence that's adequate, but actually observations in nature that were then simplified in this. And Benoit is actually giving us here that you need to actually be sure about the hypotheses and assumptions that are underpinning this model, that it isn't simply a model that works in all contexts. So looking at Gainsburg's codes that were similar to this, we found dualism, faith in one right answer owned by authority, and a recognition of the fallibility of models and the need to understand underlying assumptions. So I can add to that the idea of using the math as the coherence, so that's where the knowledge is coming from, that there's that coherence that makes it make sense, and that is how this can exist. Or actually using experiments and observation, that if it happens in the world, then that means that it makes sense, so an increased connection. Also asking them about the limits of this. So you have this equation, can you use it all the time? Are there any limits to using it? Daniel, he doesn't know any, but maybe we should ask somebody else, maybe the experts. Bernard, this wasn't where I thought he was going at all. So I say, I don't want to put words in your mouth, but it seems like you said the machine was different from the model. And he says, not necessarily. We tried to get close, but when we say 153, it isn't exactly 153. There can be more digits afterwards. It can be more precise. So the idea that an increased precision is a better model, and that if we can calculate more precisely, if we use more precise values, then in fact the answer is a better answer. So a complete lack of understanding of the model as a simplification. Cedric is able to see that the model is a simplification. Physics is very complicated, so we have models. This model is too simple, but it's what I had in my head, so I used it. And then Bart is able to give us, huge different things when you get limited. You get limited when you get down to really small proportions, and you need to think about electromagnetism or special relativity at really small time scales. So actually really being able to identify exactly what those limitations on the equations are and when they would be relevant. It's not just simple, but how it is simple and what those assumptions are. And actually we'll see an example from Bart later of actually checking these assumptions. This is, as you saw 2 slides ago from Gainsburg's model, that the fallibility of models and being able to need to see what the underlying assumptions are in those. I'd like to contribute a series of steps along the way of actually seeing that equation or the model as an absolute representation of the physical world. It is the world. Being aware that it isn't exactly the world, but really not being able to explain why it doesn't match. Expecting an increased precision would be an improvement. Understanding that these models and equations are imperfect, but being able to see their value in terms of being able to perform predictions and calculations to move that forward, but not quite at the assumptions, but just seeing it as imperfect. Another topic that came up frequently with my students was about, is there a correct answer? Are there correct answers? Is there a better answer in this context? Samuel says, for scientific problems, there will always be a single answer. If the data is wrong, then the answer will be wrong. So again, the model here is not present at all. It's just about the data, and if you have a precise data, you have a precise answer. Elise feels that if you can justify what you're thinking, then it works. That if you can explain it, explain why you took that approach, then that means that it's a valid approach, that there isn't external criteria which would designate a better or less good answer. Guillaume is aware of the possibility of several correct answers. He says that we have several indicators or ways of identifying a solution, and above a certain threshold, many of the answers would be acceptable. And with Didier, the quote that you saw on one of the first slides, that different engineers will see things differently, and that there's that judgment. aspect that's coming through in it. Gainsburg proposed that there's engineering problems have a solution known to experts and recognize the need for judgment in engineering problem solving. And so I'm proposing that in between these two, there a recognition that not just engineering problems have a single solution, but that there may be no solution or no solution yet or multiple solutions, but exactly how to manage the multiple solutions isn't clear to them. Here, the idea that there are certain criteria that will allow us to distinguish which ones are relevant, but quotes from some students here demonstrated maybe starting to recognize the need for a judgment, but not being able to put themselves in the role of being able to take that judgment. I could prepare for you information about the robot, and you could decide which of these criteria in terms of reaction time or recovery time are you going to prioritize to make that decision. But it wasn't a decision the student seemed to be able to make himself. He was talking about robots because he had a robot in his bag. Asking students specifically about assumptions, the assumptions that they had made during their problem solving. I don't have a big data set for this. It wasn't something that I apparently asked as frequently as I would have liked now. But asking students about any assumptions that they made led to really different level of awareness from students. So Guillaume assumed that the particles, this is the explosion question, were mostly in the form of a sphere or a ball, but it didn't really help him much. This is exactly the same question, but Bart says, I made the assumption that we're on Earth, choosing point 0, and so he's actually choosing to say that it's happening at a scale where I don't have to take into account special relativity or electromagnetism, that he's actually aware of those assumptions, not just assuming particles are balls. And so there's a really different level of actually thinking that these assumptions that we are consistently told throughout our studies are you need to check assumptions, but in fact, we don't need to check assumptions in the types of problems that we're given in terms of homework and exercises. They're never relevant. So it's an abstract thing you're supposed to do, but you don't actually have to do it. Not something we would do regularly. The final question for my final Think Aloud problem set, I asked a completely different question. And I asked simply how far a car could travel before wearing off a single molecular layer off of its tires. And students' responses to this were really interesting. I had students that just simply looked at the question and said, it's impossible, I can't do anything with this. Daniel gave me a list of the parameters that he would need, the weight of the car, road condition, rubber, weather. Interestingly, people who solved this problem didn't need any of those parameters. I had students who consistently said, oh, this looks fun, this is going to be interesting, but then just didn't do anything. They maybe made an estimate of the diameter of a tire, and that said that would be 2 pi r, and calculated that and stopped there. They didn't take it any farther than that, despite saying they thought it looked like fun. The students, then it made them uncomfortable. They said, they went, okay, I'm going to have to make an assumption about how far a car drives. I'm going to have to make an assumption about, and actually started making a series of assumptions. Then these students actually came up with really nice, well-reasoned answers, and that typically made reference to their own personal lived experience about trying to remember how frequently their parents changed their tires, about how far their parents would drive on a daily basis. And so looking at that in terms of the not solving it at all, giving an incredibly basic answer, a really well-developed answer, and you may have noticed this before, given that I've given you the alphabetical code to my students, we do not see a coherent development of students' abilities over their studies. And I think it's of particular concern to me that these students are doing such a poor job in their masters of being able to answer this question. So I've come up with some explanations for this. Oh, apparently I'm not going to tell you about those next. I'll tell you about those in a minute. So looking at the value of using estimates, are our estimates actually something that are a useful and relevant thing to do, or are they is it inadequate? So this is Danielle explained for this higher question. It says you really need exact numbers. And if you want to get the points on the exam, if you want to answer the question, you're going to need exact numbers. Carmen says it's okay for homework or something, but for a real explosion in the real world, you would actually need precise numbers. So not a recognition at all of estimates actually being something that are actually used in engineering practice. Bart, however, says if it's an engineer's job to create stuff, if you just solve exercise where you have the right answer at the end, then you can only go so far. So you're going to need those estimates. There's things that we don't actually know, and you're going to need the estimates to help get you to an unknown place. So this also serves to develop the model proposed by Gainsburg, who mentions estimation, trial and error, experience-based solutions at the level only of relevance. So my proposals are that correct answers need to be precise and that they're calculated from precise data. That's how we know that it's a good answer. Estimates can give a general idea, but a more precise answer is better. And that seeing estimates actually is a valuable way to move problem solving forward, and then it might be adequate, which is really different from the idea that actually real-world complexity means that estimates are actually essential and an integral part of doing engineering work, not a just maybe thing, but actually really central. Where's the slide I wanted? I hope it comes up later. All right, this is the final type of behavior that I'm going to speak to you about, is answer checking strategies. And so both in listening to students thinking aloud during their problem solving to see how they were checking their answers, if they were checking their answers, and also in response to a direct question saying, how could you check this answer? Some students, either students simply did not check their answer. You can hear her very clearly on the audio. This is my final answer. That's it. It's black and white. Cedric is doing some calculations, checking to see if they're correct and coherent, so an internal coherency. And Baptiste is actually doing an order of magnitude check of thinking, okay, he's just calculated that you can polymerize about a ½ kilo of polymer within the constraints of this polymerization machine. Does that make sense? Okay, but it's only 17 kilo mold. That's not a very big mold. Molds are really dense. So in fact, yeah, I think that makes sense. That's coherent, actually relating it to the real world. So Gainsburg mentions answer checking strategies at some really basic levels just in terms of the instructor, or using units to guide and make sense of. I think that no apparent means also falls under here. Not just using the units, but also using concepts to do some basic checking, again, with that internal coherency and consistency. Students mentioned things like substituting values back in to see if they could calculate back, or making a check again then with the general model, and then relevance here of actually really connecting it to real-world examples. In the first set of interviews, I had a question asking about how spaceships would manage to eliminate surplus heat generated from astronauts, and Didier, maybe Baptiste, no, Didier, I think, said that I don't know a lot about spaceships, so I just imagined myself in this small closed room and thought about how that was happening here. So he really put himself in the context of really imagining what those approaches were, or putting a hand on the back of the fridge, or actually really making those connections to real world and lived example. I looked at, so now I'm stepping away from Gainsburg's model and looking more at Elby and Hammer's idea of the idea of sophistication, meaning access to a broader range of strategies, not using only high-level strategies, but are they making use of everything that's available to them appropriately? And so you can see that, so the light purple is the total number of different answer checking things that they did, and the dark purple is the unique different things that they did. So this includes So actually as enacted strategies, doing things like checking with order of magnitude, checking the math, graphing it out. In terms of strategies that they said that they would do or that they did do, in other contexts included checking with peers, using a solution manual, asking Google or the internet, asking a teaching assistant. And so see that again that some students exhibited a huge number more, both in terms of the professed and enacted behaviors, and that some students really engaged in very few of these. I think that the answer checking strategies are relevant in terms of looking at students' level of sophistication, and that more strategies does not actually mean that they are less comfortable. Randalls and Overton, for instance, found that they looked at students, at industry chemists and academic chemists, and actually found that students actually check their work less than academic chemists. That actually answer checking is actually an appropriate and sophisticated approach. It is not something that naive students do. And this is coherent again with Singer's work, with just looking within a group of students, that more sophisticated students are actually doing more checking than the weaker students. But looking at the alphabet here, I've got Cedric, Elise, Baptiste, Bart, and Benoit, who are doing the most answer checking. So this is it is consistent with the tire problem that I showed you, where I don't have the most sophisticated responses coming from the students that are farther ahead in their degree studies. I also did simply using Gainsbourg's existing codes, not my contributions, but simply Gainsbourg's existing codes as a priori codes, looking at the distribution of students' behaviors across the different types of behaviors. And so I can see that almost all students were functioning in at least 3 levels, with the exception of Boris, and that students really were choosing their strategies. The most frequent strategy that students were using was at the integrating level. And this is interesting. Gainsbourg found that students the 8 students in her set actually most frequently used strategies at the dualism level. Her students were working on solving their own homework assignments, and so they actually had been in lectures, they had their notes associated with them. Whereas my students here did not, for many of them, solving sort of first-year ballistics questions was 3 or 4 years in the past for them. So they didn't have something they could readily refer to, and were functioning at a more challenging level, perhaps. So I certainly do see this diversity that Elby and Hammer have proposed in terms of, if I'm looking at the fine-grained level, which in fact I think makes it quite hard from looking at their behavior to say that they fall into a neat category. That which basket of a model would you put the students in given the diversity of their behaviors? So I've got a richer model of engineering students' epistemic sophistication in terms of what behaviors, what students will be doing, and what we could help students move forward on. That's coherent with Gainsbourg's model. I've got information about the diversity and also the relative frequency of different behaviors, which is again coherent with Elby and Hammer's model. And I think that answer checking strategies may be an interesting proxy for measurement of epistemic sophistication. I've got a very small data set, but this works to incorporate an approach both from Gainsbourg and from Elby and Hammer, and I think this comes back to my personal position in the academic, what's called the Teaching Support Center, of wanting to actually be able to offer to engineering faculty a way to actually have a sense of where their students are, and to be able to measure the impact of different interventions on students' increase in epistemic sophistication. But why don't we see an increase in students' epistemic sophistication? It's a really small number of people, so it may simply be an artifact that comes from that. The artifact also may arise from the nature of the experiment, that perhaps particularly the second-year students felt they felt more obligated to employ more behaviors, to work harder to solve the problems, that I was a more intimidating figure to them, and that they were more motivated by 15 francs to actually continue to work on solving some of the problems, whereas the master's students, it wasn't worth that much effort. And so perhaps it's simply an artifact of the experimental conditions. And previous models that have been looking at, that have found an increase over engineering studies, as we would hope would exist, were using phase models, and they weren't using the very fine approach of Elby and Hammer, and so perhaps that's part of this difference. Or it may come from the perception of engineering as a practice that is conveyed through our curriculum. So I mentioned to you earlier that I'm from an école polytechnique, with not an ick, but an eek, the difference, which is a really math and physics intensive, very abstract approach. And we really deliver a very clear message that this is really what students should be able to do, is this modeling and this abstract approach to knowledge. So I have some examples from other people's institutions of suggesting that what experts do is that they work in very abstract forms. That in fact being an expert is being able to function in that abstract way, and that our job as educators is to help students move up into that more abstract context. And so that what we're modeling for students in terms of what we want them to do, and the goal is to be more abstract. And that may actually be communicated to students as they move through their degree program to the upper levels, that it isn't appropriate for them to say, okay, well, imagine I'm in this room, or imagine I put my hand on the back of the fridge, that's actually not an expert approach to make it so concrete and individual, that remaining in a highly abstract level is actually what being an expert in engineering may look like. So an example from Baptiste, I asked him, he wrote down the formula for kinetic energy, and I asked him where it comes from. And his answer for that was, I'm not able to derive it mathematically. The formula for kinetic energy, which is describing actually a physical reality, that was not at all where he went to in terms of describing where it comes from. For him, his description of where it comes from would be a mathematical derivation. And I don't mean to suggest that he is unaware that there is a physical reality to this, but in his typical interactions with equations, such as an equation for kinetic energy, he's not actually making that connection to a physical reality. And that his perception of what I would want in the academic setting that we were in when I was asking this question is what I would be looking for from him would be a mathematical derivation and not a connection to a physical reality. So my suggestions, my recommendations for what does this mean in terms of actually teaching engineering? What does this mean for what we need to help accompany engineers in doing? Is explicit modeling of engineering thinking in terms of it being concrete and applied. That we don't do concrete and applied things like labs, like site visits, just for learning. That we often say that this is useful for students to help them understand the really abstract stuff. But this is where the goal is. And that you can do this stuff in the lab to help you get back up here. But actually understanding that what's happening in the lab is actually a really important part of it, and the way that we model those connections. Propose calculation activities that have imprecise answers, not exact answers. So propose calculation questions that have better answers, not just single answers. I didn't share these quotes with you, but the only instances in which the students discussed having homework-type problems that had multiple answers was around programming assignments, and the idea that you could construct a number of different algorithms that would give you the same outcome, but there were better routes, there were shorter routes, there were more stable routes, and that they were actually an idea in that of better answers within the coursework, and I think that might be an interesting avenue to pursue. students need to have activities where there are multiple potential models, not a single model, and where the assumptions actually need to be tested, that there's just not a hypothetical thing that check assumptions, but that it actually becomes relevant in their problem solving. And so you need to have a clearer idea for your own students in your own context of what is your students' perception of the knowledge in your course and what it is that they should be doing with that knowledge. So, through the development of a specific set of tasks that are quite contextualized and were accessible to students throughout their engineering degree programs, I have something of a measurement instrument for looking at students' epistemic conceptions. I have Gainsburg's model seems to be relevant in our context of Francophone University in Switzerland, and I've proposed a number of additional characteristics to deepen and enrich that model. Elby and Hammer's model also seems to be relevant in terms of the variety of different strategies that students are exhibiting in their problem solving, and that there's really a range of different behaviors. And if I'm lucky, then answer checking will turn out to be something that may be more easily quantifiable in terms of being able to provide a less intensive way of providing feedback to engineering faculty than long interviews. So thank you very much for your attention, and I'm really looking forward to questions and additional insight in our exchanges. Thank you.
Thank you, Siara, for that really rich and engaging presentation. I think the way in which you gave such a thoughtful account of the complexity of what you're trying to look at, and the sort of clear sense of the struggle of trying to find ways to get to that complexity was just really refreshing, and I thought it was great. So thank you for that. So we'll now move into questions. If people want further refreshments, please help yourself. A reminder that people on the live stream would like to hear the questions, so if you can make use of the microphones when you ask. And if people on the live stream want to ask a question, then an email to edresseminars@lancaster.ac.uk, all lowercase with a double S in the middle of Edres Seminars, and then Rebecca will pass on the question on your behalf. So who would like to kick us off with a question or comment? Jan.
I will. Thank you for that. That was really interesting. Obviously, I'm not from this discipline, so I hope this question isn't silly. But have I understood correctly that as one increases in expertise, one is operating at a more abstract level? But is that same? You made an earlier point about estimates, and I'm just really interested if they're working with estimates at an abstract level.
So I think that in fact that actually practicing engineers are actually need to move from the abstract into the really concrete, and that there may be a need to move in both directions. But that in our teaching of engineering, we tend to help students move to the abstract and move to the abstract and move to the abstract. So what we convey to students about what they should be doing is being abstract, but in fact in the practice, it's actually about moving both directions. So I don't think that a practicing engineer in the field functions in the abstract, because they need to not just know about the model for, but to actually decide, given the muddy water that I'm standing in up to my knees, does that model fit here? Not that there is an expert model.
Okay.
I'm not sure if that was a...
No, I think it clarified my misunderstanding, yes.
But we are you are from this field. I'm standing here in educational research.
I don't know much about that either.
Did you notice many differences actually within the different specialisms within engineering? You mentioned in the sample it was quite a broad one with various sort of specialisms represented. Was there any difference sort of between the specialisms, as it were? And I suppose what's also in my mind is in a way, does if you're following a more general engineering degree, does that offer a sort of different insights compared with a more specialist one?
What's a general engineering degree?
Oh, I suppose I'm also getting out of my but I suppose I'm talking about the difference between somebody who's doing a degree in civil engineering or something, compared with somebody who's doing a more broadly based engineering degree that may well have elements of electrical, civil, mechanical, chemical, and so on.
We don't let them do that. We don't let them do that. They do microengineering or environmental engineering or civil engineering, and
right.
keep them in very tight boxes.
But I come back to my original point then. Is there did you notice any differences between the different sort of groups that you mentioned?
I would be really interested in looking at that. However, I have, out of 19 students that I interviewed, they're from 12 different backgrounds. From the first year through to master's, so they're from a variety of different specializations. Some of them are students that have been with us for a bachelor's and a master's. Some have entered our institution at the master's level. In terms of the intake, the bachelor's level mostly comes from about 70% Swiss, about 30% French. And then at the master's level, it's more broadly European again. And so between the different disciplines, the different years, and the different backgrounds of students coming in, I don't have I can't say anything about anyone other than as an individual. But would I love to have that quantitative data? Yes.
Yes.
But I'm not there.
Okay.
Then I could do stat. That's not happening.
I really enjoyed that. I think it was great. I was just wondering whether there were some students that seemed to have the more sophisticated models, and whether that was reflected in their grade and how they were doing the program, or whether it wasn't at all.
In general, I didn't ask students about their grades. I do know that for Bart and Benoit, who really exhibited really quite exceptional behavior, we have an interesting system where we actually don't have any selection criteria for incoming students. That if students have a high school leaving certificate from Switzerland, they can come. But we also have a pass rate of about 50% in the first year. So the first year is quite drastic. And I know that for Bart, he got the equivalent of, I don't know how you grade here, we grade out of a 6-point scale, and he had a 5.5 in a year that has 50% fail rate. So he had, I know he had very, very, very good grades. I don't know for anyone else. I don't know if that type of awareness that he's exhibiting, though, is useful at all for him at the undergraduate level. I know that it will be, but I don't know if that actually does help him with his coursework now.
Me, not online. How did you decide the problems that you posed to the students? How did you decide on those particular problems? Is there a sort of set of problems that they always use in those circumstances, or you have to fit in?
No, I created them. No, the tire question I found, but the other questions I created. So they're more typically sort of chemistry-ish, because that's something that I can do, and enabled me to also be able to see how they were going about approaching them, that I was able to do that because they were chemistry. I wanted them to be challenging enough that it wasn't obvious to students on how to solve them, and that there was the information necessary in them to solve it. In the questions around polymerization, for instance, those questions worked really well because as engineers, they do quite a lot of thermodynamics. So they work with heat capacity quite a lot, and all this stuff was in there for them to be able to use the units to put it together and to actually come up with that equation. So I was trying to create problems that would require, that they would write down equations for, that they were able to solve, that they weren't able to solve in a really obvious way. Some of the students were able to solve one out of the set very easily. I'm like, oh yeah, we did a lot of these last year, and that wasn't that interesting to me. But no one is able to solve all of them like that. So, and slightly trial and error. Starting, of course, experimenting on my colleagues to develop the questions, yeah.
Can I come back? So, having sort of, got your understanding of what the students see as knowledge and so on, taking it up a level, what do you feel are the main lessons from this work, which is fascinating? What do you see as the main lessons from this work for the overall sort of design of engineering degree courses? And I'm thinking of both, content, but also the sort of development over the period of a degree program. What do you see as the main sort of implications for course design?
So we come from, my institution is a Polytechnique institution, and so that's a very different approach from, for instance, from a problem-based learning approach in engineering, which is common in engineering curriculums, or a CDIO model, the conceive, design, implement, operate model, which are two really different, much more concrete and applied models. And so I think that it may be something that's interesting, that it would be interesting to think about. Is this something that is representative of students thinking about in a polytechnic? Is this something that's done differently in these other models? And is that something that would be interesting to think about how the polytechnic model could do this better? And maybe it already exists in a problem-based learning or CDIO model. But I think it really is about making that connection between the practical, and that the practical isn't just something that, we have you do really basic things in the lab so that you can do this abstract thing, but that the stuff when you have your hands, when you're actually touching the components of the circuit, that is actually the engineering, that the engineering is not just when it's modeled in a very clean, concise way. The messiness. I think in general a lot more messiness. Messiness of estimations, imperfect assumptions, to have more mess, and to in a couple of different instances, the students explained to me that engineering is about simplifying, that engineering is about making it very simple and clean and removing things. And in fact, when you actually contextualize it, it becomes very messy and authentic. And to actually keep that in, and to not have just the words in English, the simplification as the goal in it.
Yeah. Do you think PBL does that differently? Do you have a sense of that?
PBL certainly does. It has a huge amount more contextualization. That the problem that it's not that students are typically working in the context of something, and I think that there's a range of the degree of problems. For instance, the Alberg model, the problems that students are working on tend to be semester long, often for a client. So they actually really are very contextualized and very complex. The PBL model, as it's implemented in France, tends to be more, it's a problem on paper. So even within PBL, it can be quite different.
Just to kind of follow up to my first question, I think some of you have answered. It's about the extent to which the assessment methods kind of reflected your models. So, for example, somebody who had kind of very unsophisticated understandings be doing really well on the course.
I think in some cases to not do too big a detour, but there's work that I find quite interesting from initially American work published by Richard Haig in the Journal of Physics Education, using the Howland-Hastings mechanics diagnostic test. And he looked at high school, college, and university level students, a total of over 6,000 of them, of the pre and post test, and found that in many cases students were not really improving in their conceptual knowledge, that they were able to solve very complex physics calculation problems, but actually their conceptual understanding really wasn't improving. And so we did a study at EPFL well, quite a while ago now, maybe about 5 years ago now, where we had students do the same thing, the pre and the post test. And we actually found that, that actually any students that were passing the first year exam actually had that high level, did have the conceptual understanding. So they were not passing without the conceptual understanding. So it does seem that that part, in terms of the conceptual understanding, that part is really there. In terms of it being really anchored, I don't know. But we did not, as was found in a number of other instances, that actually students were passing the exam because they were able to do the complicated calculations without the reflection. We did not find that in our students.
It was really interesting to see the development of strategy in terms of solving all those questions. So, then this question came to me that, then if you ask the same question to the teachers of that courses, then how do you think they're going to answer to the question? Do you think they're going to give you the same answer? I mean, do you think they're going to be more sophisticated than the teachers and students?
Yes, absolutely. I think that that the teachers are absolutely aware of the connection between the abstract and the concrete. But whether or not that's the part that my concern is that that's not the part that they tend to model during their teaching. I know that they know that they have those connections and that they use those connections within their own experimental and research work. But that's not what they're modeling in terms of modeling their thinking when they're talking to students about problem solving, about how to think about things. I don't think that that's what's coming out. I don't have those observations. I think that'd be a really interesting thing to look at.
And also then, if a student reach this highest level in terms of sophistication of epistemological ideas, and that student can be evolved into the first stage maybe? Or is it impossible? Is it just one way development, or can it be iterative?
So I don't think it's. I don't think that people tend to go back to looking for an expert as the sole source of knowledge, for instance, within a given discipline. But there is some suggestion that when somebody moves to a new discipline, for instance, that you may have quite sophisticated beliefs around engineering, but if you don't cook at all and you're going to learn how to cook, you may think that you have to follow, it says 2 eggs, and if I don't have 2 eggs, I can't do it. And that you really, that you are quite rigid, and you really look at the expert before realizing that, and becoming more sophisticated in your approach to cooking and enabling yourself to broaden that. So there is, that when you change, that it is discipline specific, and that when you change disciplines, you may not be as sophisticated in another context as you are in this context.
I was interested that in a way you could see your think-aloud tasks as a form of assessment. And it was a form of assessment, we're trying to assess their understanding and their approach. And whether, how that maps onto the way they're actually assessed in their degrees, and the relationships between those forms of assessment and what that might illuminate.
Yes, so I was interested in seeing how they were going about the task, but I really stressed to them that I was not interested in correct answers. That they should take these. That although I tended to sit in the same room, that I made sure that I was busy with something else and I was able to hand them the next task as they completed it, but that they should put themselves in the context of working on it, a set of exercises, that I would manage the time. I didn't want the right answer, and I really wanted to stress that to them, that this was not to feel that they were in an assessment situation. Because I was really interested in the path, and that's what I told them, and that in fact is what I'm interested in. And I think that that's a really big difference in terms of the way that they're assessed. I think, in fact, the problems that I asked them were much simpler than the problems that they're typically assessed on, because I needed them to fit for everybody. So the problems were more difficult, but I want to know about the stuff that they were doing along the way, and asking them about why they did what they did. And that's not that we were very interested in final answers, and maybe demonstrating how you got there, but how you got there mathematically, not about how you checked your answer by connecting it to. I want to know that you've connected that you have a correct value, but how you're going to use strategies to make sure you get to the correct value, but I'm not assessing at all what you're doing to get there.
So the assessment system within their courses rules the text they produce, not the process by which they produce those texts.
Absolutely, yeah.
Which in a way would fit with what we found, because if you were rewarded for being able to produce something without a sense of how it was produced, then there seems to be...
Or if you need to demonstrate how it's produced, that is a mathematical. The way it's produced is mathematical. It isn't produced by making those connections. Or if you do think of those things, that's not something you don't write down. You don't say, I thought of changing gears on my bike. You don't write that in your calculation. I was interested and disappointed to see if asking students about the mental models that they used, did they when they thought of this, when they thought of the problem solving, what did they see? And so, for instance, for the tire question, one of my students said that he saw the car in the CATIA software for engineering design. Or did you see a schema? Did you see a movie? Did you see like a textbook illustration? What did you see in your mind? And I thought that might have been again, an interesting indicator, simple indicator of the authenticity of their problem solving. No dice. No, random. Anyway, on my very small sample, totally random. No.
Okay, well, we'll leave it there. So thank you, Siara, for such an engaging seminar. I think what's really nice is we've got that meta relation of you looking at the students' problem solving, but also giving us a sense of your problem solving and trying to understand their problem solving. I think that came across really nicely, and there's something really nice about that relationship. So thank you so much. This is the final seminar of this year. Next seminar will take place in October 2019. The room's still available if people want to come and ask Siara further questions. But finally, you can thank Siara for such an engaging and thought-provoking seminar.